Okay, one section down, the next section, 9.2, the actual process of chemical equilibrium. So one of the things that this doesn't have is we have to understand that chemical equilibrium is quite dynamic, okay? And what I mean by dynamic, to have chemical equilibrium, and I say it's dynamic, I like to tell people one of the criteria is you have to have a closed system. Okay, I want you to keep that in mind. You have to have a closed system. If you don't have a closed system, it won't work. Okay, so you have to have a closed system. That way these gas particles can't escape. Okay, because that would change the equilibrium process. So these are stuck in a container. All right. So let's say I have a closed system and I have some gases. And suppose I start with sulfur dioxide and oxygen. Okay, so I have these two. And as they collide in the 2-to-1 mole ratio, eventually some of those collisions are going to be effective. They're going to have enough kinetic energy and they're going to be in the right orientation where they're going to actually produce 2 moles of sulfur trioxide. Okay. Now realize at first I have a lot of reactants, but as time goes on, I have fewer reactants because at first I have no products, and as time goes on, I increase the products. So some of the reactants are being converted to products as time progresses. But as the SO3 forms, so as the sulfur trioxide, what appears to be the product begins to form, now they actually begin to collide with themselves. And when they start to collide with themselves, they can go in the reverse direction because this is a closed system. Remember, the gases, if they're in a closed system, they can't escape. So if the products now start colliding, we can start seeing them going backwards. And that's why many of your reactions show a double arrow. The double arrows to represent that there's a forward reaction and there's a reverse. And if you think about it, this is the case in your body. You're, I mean, you have openings, obviously, but you're pretty much a closed system. So you can have forward and reverse reactions, right? So, and that's good. You want to be able to have forward and reverse reactions. You want to have things, so like when lactic acid builds up, you want it to go in the reverse reaction, form those acetyls, those acetyl groups when oxygen's present, and then go back into the Krebs cycle, which is an aerobic process. So when there is no oxygen, the acetyls are converted to lactic acid, and that's why you get sore. When there is oxygen, thankfully, we can go in the reverse direction. The lactic acid can be removed, converted to acetyls, and then form into the Krebs cycle. So you have to realize that in closed system, you can have that occur. So what does that look like? Well, the rate of the forward reaction eventually will become equal to the rate of the reverse. So how does this diagram help me see equilibrium? Okay, so at first, if I'm looking at the y-axis, this says how fast things occur. And as we move up the y-axis, things are occurring a lot faster. Okay, so we could say here, you know, there is no reaction rate. But as time progresses, okay, we start with a lot of reactants, right? So at first we have a ton of reactants, okay? And because all we have are reactants at first, the rate of their forward reaction is really high because that's what's colliding. But as they collide, more of the product is produced. So you're getting less reactants as they get used up, and eventually their rate stables off. And now they're colliding at a consistent basis. If you look at the reverse reaction, so products, at first there's no products. So their rate is very low. They're not colliding, they're not producing the reverse reaction, the reactants. But eventually, as more is being produced, it kind of tapers off and levels off. Okay? So the rate of the forward reaction becomes equal to the rate of the reverse. That's what equilibrium means. It's when the rate of the forward and the reverse reaction are the same. What I don't want you to get confused, it doesn't mean that you have the same amount of products and reactants. That's not equilibrium. Equilibrium is not looking at concentration. It's only saying well, it is looking at concentration, but it's not saying an equal concentration. It's saying an equal rate of the forward and reverse reaction. So when equilibrium is reached, right, if you look at concentrations, they may not be equal. So at first, again, the brackets, okay, these brackets typically mean molarity. And molarity is concentration. It's one of the ways we measure it. It's moles of solute per liter, and we see that here. So at first, I have a lot of moles per liter. So I have a lot of reactant particles per unit volume. And as time goes on, they collide, they get used up, and they're producing products. So eventually it kind of stabilizes on how often they produce the products. Initially, there's no product, but as the reactants collide, I increase the amount of product until eventually it also stabilizes. And when everything stabilizes, where the concentration of the reactants and the products no longer change, that's what equilibrium is. It's because the concentrations don't change. So there is no further change in the amounts. Now, what a lot of people struggle with this concept. They don't understand how is it that I can have equal rates of reactions, forward and reverse, but different concentrations. So this is it's kind of a cheesy analogy, but I hope it helps, okay? So you can think of, there's a club. And in the club, right, you can only fit 300 people, okay? And then outside, there's a line. And in the line, maybe there's 100 people waiting in line. You can't get inside the club because the club only has a 300 max occupancy until 2 people leave. So when 2 people leave, right, 2 people from the line can go inside. So it's equal rates, right? So you always have the same amount of people in the club. So you always have the same amount of concentration, but the rate, so people leaving and people entering 2 and 2 is always the same. So again, that's kind of a cheesy analogy, but maybe that'll help you understand it. So what we do know is because the forward and reverse reaction rates end up being equal, the concentrations of the reactants and products typically can kind of be compared in a ratio. And that ratio or that quotient is called our equilibrium constant. So we can look at the concentrations of reactants and products and put it in a quotient and say that there is some constant. There's some direct proportionality for these substances. And that's what equilibrium constants do for us. So the equilibrium constant is referred to as K. So K of equilibrium. When they put a little subscript of C, as they do here, that's to represent concentration. So brackets, again, if you look at the brackets, that's molarity. And molarity is a measurement of concentration, moles per liter. So the lowercase c represents concentration. The capital K is my equilibrium expression. So if I have a balanced equation, the first thing I want to do is there a double arrow? If there's a double arrow, that means it's in a state of equilibrium. I could have a forward and reverse reaction. If it's in a state of equilibrium, I can write out a quotient or an equilibrium constant to represent the concentrations of this equilibrium equation. So how do I do that? It's basically the product concentrations in the numerator and reactants in the denominator. I always tell people, just think you have a ratio, products over reactants. Just remember that ratio, products over reactants. Now, it's not that simple. It's a little more complicated, but if I remember products over reactants, it becomes a lot easier. So in this case, the product, and I have a squiggle there so it's hard to see, the product is CO2. So I notice, and they put it in brackets, because again, brackets measures concentration in terms of molarity. They have bracket CO2, because that represents the concentration of the CO2 gas that is a product. In the numerator, they have the concentration of the reactants. So they put in brackets carbon monoxide and oxygen gas. However, if we look at balanced equations, there's not just the species that are involved in the reaction. And that's one of the things that we learned in chapter 5. We had to balance chemical equations. So we have to use the mole ratios, the coefficients that we use for balancing chemical equations as superscripts. Now, I almost don't like this term superscript. I prefer the term power, or maybe you don't like the term power, exponents. Okay, so we are going to use the coefficients in balance equations as exponents for the concentrations of the substances involved in the reaction. So CO2 had a coefficient of 2. So what is the exponent for CO2? 2. Why? Because it has a coefficient of 2. I look over here, carbon monoxide has a coefficient of 2 as well, and I notice that coefficient is right there as an exponent. And then the oxygen, it's assumed, I mean, it's not written here, but it's assumed, right? If it's not written, there's 1 mole of it. So the exponent here would be a 1. So that's essentially what you're doing to represent equilibrium constants, right? So if you want to write out an equilibrium constant, which is what this is, which is relating the amount of products and reactants, okay? So the equilibrium constant is relating the concentrations of the products and reactants at equilibrium. You put it in a ratio, a quotient, and it's products over reactants, and we use the exponent or the coefficients in the balance equation as exponents. So let's see how you do with this one. I'll give you a second to kind of look at this and figure out which one you think. So I'll just give you a little minute here. All right, so again, this problem is asking for us to write out K, and the subscript C is representing the equilibrium constant in terms of the concentrations of the products and reactants. So really, the equilibrium constant is kind of representing a proportion of products to reactants. And that's essentially what K is. It's the equilibrium constant. So the quotient, what's going to help you remember that quotient? What did I say it essentially is? Does anybody remember? What's the quotient? Like, what's an easy way to remember it? It's an easy way to remember the quotient without looking at even, what's in the reaction. It's an easy way to remember that quotient. You don't even need to look at a reaction, right? Because it's a ratio.
Is it products over reactants?
Yes, that's exactly what I was looking for. Just remember products over reactants. That's exactly what I wanted you guys to say. So we know it's got to be products, right? We're looking at the concentration of products over reactants, okay? And once we do that, it makes our life a little bit easier. Doesn't seem so overwhelming. So now I go, all right, K of equilibrium. I'll put a C there. You don't have to, but I will. And I know it's a ratio of products over reactants. So now I have to be specific for this reaction. So I look, what are my products? Nitrogen trichloride. So I put that in brackets because that represents concentration molarity. And there are no other products. So what goes in the denominator of this quotient? The reactants. So I look, I have two reactants, so I'm going to put them. Nitrogen is one, and chlorine is another. But if I truly want to represent, right, a proportionality for these concentrations for this reaction, what do I have to take in account also?
The power or exponents.
Yes, I have to take in consideration the coefficients. And I said those coefficients have to be changed to exponents, right? I don't like saying superscripts because people get confused. But if I look at my products, right, nitrogen trichloride, there is a coefficient of 2, so I make an exponent of 2. If I look at my reactants, right, nitrogen, there's just 1, so I don't need to write the 1, it's assumed. But I look at the chlorine, there's a 3, so my chlorine should have a power of 3. So which one would work?
4.
And you are right. You are exactly right. So what we did in this first portion of this lecture is we discussed, well, okay, how does a reaction take place, right? You have to have enough activation energy. Well, what is activation energy? The minimum amount of energy required to break bonds so we can form new ones, and it has to be in the correct orientation. We talked about things that can affect reaction rates or affect how quickly we meet that transition energy. And basically, the way I want you to look at it is we discuss things that will influence the number of collisions. So one was an increase in temperature, another one was an increase in concentration. And then we talked about how catalysts lower activation energy because they provide the correct orientation so it can speed up the process. And we essentially defined equilibrium as when a system that is closed and dynamic, when we have the forward and reverse rates occurring at the same speed, doesn't mean the same concentrations, but it does mean at the same rate, you create what is referred to as dynamic equilibrium. And then the last part of this lecture, we kind of show, of this portion of the lecture, is we showed, well, how can I represent this dynamic equilibrium? What can I use to show how the products from the forward reaction and how the reactants from the reverse reaction, how can I show their relationship? And we showed it using the quotient of the K of equilibrium, which is products over reactants, the concentrations, and using the balanced chemical equations coefficients as powers.